Okay, hello. I'm Gavin Ferris. I'm CEO and co-founder of Low Risk CIC, and I'm very happy to be here speaking with you today. So Low Risk is a UK-based non-profit company. We have a full-stack silicon engineering capability, including digital design, design verification, security analysis, and firmware and toolchain development. And we were founded 10 years ago as a spin-out from the University of Cambridge Department of Computer Science and Technology. And we have a rapidly growing team of 30 staff, with offices in Cambridge and Zurich. And also our wholly owned subsidiary, Canadian NewAE, develops security evaluation hardware, and I'm proud to say they'll be hosting CHES 2024 in Halifax later this year. And Low Risk's a founding member of the RISC-V Foundation, now international, and also of the Cherry Alliance. And we're stewards and maintainers of the OpenTitan and IBEX projects. And our mission is to help make open source silicon designs a reality, commercially relevant and widely adopted throughout the industry. And I'm happy to say we've reached a major milestone in that journey with the first commercial grade, fully open source silicon developed with our partners and heading into its first socket, Chromebooks. So I'd like to speak a little bit today about what has been achieved, why we believe it's of significant importance to our industry, and how the Silicon Commons methodology has made that possible. And of course, a little bit about what comes next. So, development of the open, clean RISC-V instruction set architecture was, of course, a hugely important enabler for this. As an ISA defines how hardware and software interact, there can be no truly open silicon without an open ISA. And with the initial RISC-V specs cohering at around the same time Low Risk was started, it was a natural choice for us to leverage. That said, while the ISA is vital, it's only one component of a silicon design, and our goal has always been to open up as much as possible of the traditional silicon IP stack, and do so with real use cases, working collaboratively with corporate and academic partners to achieve maximum real-world impact. And our flagship open silicon project is OpenTitan, and it's the world's first open source silicon root of trust. We steward and contribute to that project, which was started by Google over 5 years ago, and has been worked on collaboratively by a set of major partners and contributors that you can see listed here. And in OpenTitan, we've taken a pragmatic approach to open source silicon with a focus on ensuring that all RTL and design verification DV collateral is available under a permissive license, while using industry standard tools, languages, and manufacturing technologies to meet commercial standards. So we're not, for example, trying to reach below the foundry boundary, replace System Verilog with something else, use exclusively open EDA tools, et cetera, et cetera. So getting to this degree of openness, which we think is significant, required quite enough engineering effort as things stand. And although it's been a long journey, I'm delighted to say that commercial grade, fully open source silicon has now arrived. So the OpenTitan project, which as noted has been driven by a group of 9 partners and hosted by Low Risk, announced a successful engineering sample tape-out of its initial Earl Grey part, shown on the slide in February this year. The production design is now in RTL freeze, with volume scheduled to ramp up in 2025. The chip will be sold by Taiwanese vendor Novaton, and the initial announced socket is Google Chromebooks, where it will ultimately replace their existing closed-source silicon part. And an open market version of the OpenTitan chip is also being made available. So it's really exciting to see an open silicon solution being produced, adopted by a mainstream platform, and paving the way for future use. And the economic benefit for everyone is, of course, clear. High-quality foundational security IP should be widely available, particularly in an era where cybersecurity liability is rapidly increasing. For example, the EU's CRA and NIS2 legislation is now rapidly coming on stream. So, how did we achieve this? Well, through our Silicon Commons methodology, which we also developed together with our project partners and contributors. Now, open source software, of course, has already taken the world by storm, so our approach adopts many of the successful elements of that. However, critically, silicon development is different from software with much higher barriers to entry. There's a physical supply chain to reckon with, far fewer skilled engineers. There's high cost of EDA tools, mask sets, and the need for eye-watering amounts of upfront testing or design verification DV. Because release early, release often doesn't work for silicon. A brick is a brick is a brick. So although we have learned from and leveraged the best parts of open source software development, so yes, we have code reviews, RFCs, coding standards, etc., we couldn't just adopt it wholesale. Instead, with our partners, we've evolved it into the Silicon Commons. As you'd expect, this includes design guidelines, training and documentation, but also a rigorous governance process and infrastructure elements such as continuous integration, CI, regression testing frameworks, and so on. Now, of course, getting silicon security and firmware engineers from multiple companies working together outside of their traditional waterfall development pattern has been challenging. So, does it all work? Well, yes. Not only do we have an existence proof with Earl Grey silicon successfully taped out and heading into Chromebooks, with many more use cases we hope to follow, and not only is all the design, firmware, and DV test collateral openly available on GitHub for anyone to review, download, and reuse under an Apache 2 license, with OpenDV dashboards, extensive documentation, and full provenance as well for all IP blocks. But we're also proud to say OpenTitan's become the world's most active open source silicon project. In other words, there's hard proof from multiple angles that the Silicon Commons approach delivers the goods. So OpenTitan has three foundational pillars or principles. So the first is quality, and that's visible through our commitment to documentation, review, and perhaps most importantly, DV. A huge amount of our code base is associated with test. The second is flexibility. So OpenTitan is not just one design, but an ecosystem of high-quality building blocks, which, as we'll see shortly, can and have been recomposed into different top levels. And the third is transparency. So look, we're firm believers in Kirchhoff's principle that the only thing that you should need to keep secret in a well-designed crypto system is the secret key material itself, but there's more to it than that. Through our partners, third-party labs, and with the assistance of wholly owned subsidiary in UAE, the OpenTitan partnership has ensured that the RTL and firmware has been tested and hardened against side channel leakage and fault injection attacks and many other vectors. And finally, we should just note that OpenTitan supports PQC signature verification out of the box with Sphinx Plus. And the fact the whole system is available has, of course, encouraged many security researchers and academics to run their own experiments and tools against the design. And that's a great benefit of having the IP open. And we're happy to say that the design has been able to integrate many of their suggestions and has improved as a result. So it's truly a win-win. Now, as to timelines, well, as I said earlier, developing silicon's a long road, particularly if it is to be done to commercial grade. And as the OpenTitan project did, starting with very little to no existing IP in the permissively licensed but commercial grade parts bin. So it's been quite a journey, 5 years and under a reasonable metric around $100 million to get here. But commercial grade, fully open source silicon is now a reality. And from here, with the activation energy threshold satisfied, if you will, things will really start to move ahead at speed. So let's just drop down a little bit and look at, in some detail, at the first developed OpenTitan top level. That's called Earl Grey. Apologies for all the T names, and blame us Brits. And that's a discrete chip design. It's a low-power, secure microcontroller designed for security-critical applications. For example, system root of trust. Onboard flash, significant architectural security features such as dual lockstep core, and abstracted wrappers around key process-specific elements such as OTP, analog sensors, and so on to ensure flexibility in choice of process node for implementation. And the OpenTitan Coalition continues to work in unison to accelerate the project's momentum and demonstrate the flexibility that's inherent in that ecosystem of recomposable IP blocks. And so we have another top level, codenamed Darjeeling, which is designed to be incorporated as a secure execution environment within third-party SoCs and chiplets, in contrast to the standalone or discrete Earl Grey top level we just saw. And we released the first public version of Darjeeling in November last year, and an upcoming milestone will be the full release of that. As you can see, many of the IP blocks are shared between the two top levels, but because of the much smaller feature sizes, order of magnitude higher clock frequencies, the reality of being hosted inside a larger system, some blocks are not carried across, some are modified, some are new. For example, you've no on-chip flash, you need DMA, mailbox support, etc. And Revos, who raised a $250 million funding round in April this year, and are OpenTitan partners, state publicly they're integrating OpenTitan IP directly into their system silicon. And in fact, they've been major contributors to Darjeeling, and they've also open sourced their QEMU models for the design, which is something we're very grateful for. And lastly here, another version of Darjeeling, codenamed Chai, is in the works, which includes a secure flash interface. So very low feature sizes, obviously there's no on-chip flash, and so being able to interface with, for example, project partner Winbond's secure flash solutions in a PP117 compliant fashion is a really valuable feature. So look out for that. And if we had to pick one great illustration of the project of building together, building well, and building securely, or open source silicon working as intended, if you will, it would have to be the IBEX CPU core that's used in both Earl Grey and Darjeeling. It's a highly configurable RV32 IMCB core with a number of integrated security features as shown on the slide. And the story is quite interesting because it was initially contributed into the OpenTitan project by ETH Zurich, our partners, as zero-risk scheme. And with our partners, we helped optimize, harden, and verify it, evolving the offering into IBEX. And IBEX's flexibility, security, and excellent toolchain integration, plus the availability of an FPGA demo system, permissive licensing, and so on, has led to it being adopted by many companies and university users. And without breaching any NDAs, suffice it to say, IBEX has been taped out in many commercial designs already. In fact, you'll also see it in many of the posters at this very event. And Low Risk offers paid commercial support for those wanting to leverage this well-proven microcontroller core in their own designs. But the story doesn't stop there because Microsoft independently selected IBEX as the reference platform for their Chariot development. Now, Cherry, as many of you know, is an ISA-independent hardware security technology. It was developed by Cambridge University and SRI International, and it provides strong memory safety guarantees, spatial, referential, temporal, and low-cost compartmentalization. And those are particularly relevant features for legacy code bases, not written in modern memory-safe languages like Rust, but older languages such as C and C++. And there's a lot of that. It's conservatively estimated a couple of trillion lines of code have been written in the last 20 years, and the vast majority of those not in memory-safe format, and they're not going to get rewritten anytime soon. So Chariot IBEX offers a RISC-V 32-bit, very low overhead implementation of Cherry, so compared to a vanilla IBEX system, unchanged Fmax, 10% penalty in speed and area. And last week, Low Risk was pleased to announce that we're working in partnership with Microsoft to help bring Chariot IBEX to production grade, collaborating with them on delivering a full suite of DV that will allow users to confidently incorporate and leverage the IP in commercial designs. And to further encourage adoption of this exciting technology, Low Risk has been working with UKRI and DSBD, Digital Security by Design, on the Sunburst project to create fully open source platforms that enable users to evaluate Chariot IBEX in advance of silicon availability. And a particular focus here are domains where power and area and budgets are tight, such as operational technology, embedded systems, and IoT. The first of these platforms is Sonata. It's an FPGA-based development board and accompanying RTL, firmware, demo software, and educational materials. And as part of that Sunburst project, we're also developing Symphony, which combines the Sonata system with a full OpenTitan root of trust. So if you're interested in finding out more about the project, please visit the talk by Low Risk digital design lead Greg Chadwick, which is taking place in the demo theater at 3:10 p.m. CEST today. So in conclusion, we're at a very exciting juncture now for open source silicon. With validated commercial-grade ES chips in hand, first announced commercial sockets for the production silicon in Chromebooks, a first public design win for the integrated IP with the pocket NVIDIA company Revos, and with many from universities to industry giants like Microsoft looking at the corpus of IP our partners have built collaboratively alongside us, finding it good and extending it and adopting it in novel ways. Which brings me to my final thought. Open source silicon enabled at the outset by the Open RISC-V ISA is now at a watershed moment. The costs of silicon mean that true commercial-grade open source IP has taken a long time and a lot of investment to create and has required a modified development flow, the Silicon Commons, to really set up and work. But we're here now, the activation energy has been satisfied, And I suggest to you that we know from our predecessors in the open source world of software how the movie ends. And spoiler alert, it's not a tragedy. Open source will not spell the end for commercial silicon designs and vendors, just as open source software didn't. Rather, just as there are designers looking to get to market quickly with the best possible, most competitive products, will leverage the high-quality IP from the open source domain, avoiding reinventing wheels, and instead concentrating their scarce DD, DV, and firmware resources on making novel USPs that are truly secret sauce and value additive. So in short, it'll enable everyone to do more with less, faster, better, more securely, whilst also enabling our partners in the academic domain to contribute more fully to the state of the art. So what's not to like? Well, if that sounds interesting, Luris can assist your company in its journey to leverage open source silicon too. So whether your focus is on design, DV, integration, tooling, or support, reach out and start a conversation. Our door is always open. So join us and build together, build well, and build securely. Thank you.